This video will instruct you on the function of the resistance motor and how machines employing silent magnetic resistance generate the resistance felt by the user while pedaling. There are certain parts of the resistance system that are common to almost all current design bikes and ellipticals. These include a console, wire harness, resistance motor, resistance cable or link arm, and a resistance mech or some other variation of flywheel and magnetic bracket. In this video, we will look at a common resistance mech. When the user presses a button on the console to change the resistance, the console sends a signal to the resistance motor. When the resistance motor turns on, it will either wind up or release the resistance cable depending upon if the user wants to increase or decrease resistance. On units with an internal eddy mech, the resistance will increase as the motor releases the resistance cable. When the resistance cable is released, it allows the magnet brackets within the mech to move closer to the inside of the flywheel. Although the magnets are not visible, you can see the cable slider on the mech move upwards as the spring tension magnets are allowed to move towards the flywheel. When decreasing the resistance, the motor winds the resistance cable onto the motor, pulling the mech cable slider downward toward the center of the mech. This in turn pulls the magnets away from the flywheel, decreasing the resistance. You can see here how the magnets move away from the outside of the mech as the slider is pulled towards the center of the mech. The closer the magnets are to the flywheel, the more resistance is generated and felt by the user as they pedal. You can make small adjustments to the resistance felt at each resistance level by adjusting the length of the resistance cable. Typically, we hear that the resistance is too hard even at the lowest resistance level. To make some adjustment to the resistance cable, loosen the small nut away from the large barrel nut on the resistance cable. Turn the barrel nut so that it unthreads from the elbow in the resistance cable. This lengthens the distance in the cable sheath so that the slider is pulled further towards the center of the resistance mech, pulling the magnet slightly further from the flywheel. Once the barrel nut is in the desired position, tighten the smaller nut to lock the barrel nut into place. Although the magnets never come into contact with the flywheel, they are able to generate a great amount of resistance. This is because of the electrical energy created in the flywheel as it passes through the magnetic field of the mech magnets. This energy pushes against the magnets and creates resistance felt by the user. This is illustrated in the following demonstration. Even though the copper pipe is not magnetic, it is a very good conductor of electrical energy. You can see that the steel nut passes right through the copper pipe. You can also see that even though the copper is not magnetic and the magnet is not attracted to it, the magnet fall is slowed as it is dropped into the copper pipe by the same forces that cause resistance in our eddy mechs and other machines that use silent magnetic resistance. The resistance motor has two main functions. One function is to wind and release the resistance cable. The other function is to report to the console how far the motor has rotated so that the console can tell what resistance position the magnets in the mech are in. All communications to the resistance motor and console occur along a 5-wire harness. When the user presses a resistance button, the console sends voltage to the motor across the yellow and blue wires. Whenever there is voltage on the yellow and blue wires, the motor will rotate. The polarity of the voltage can either be positive or negative. The direction of motor travel will depend on the polarity of the voltage being sent by the console. We can see this by using a voltage multimeter by putting our probes on the yellow and blue wire pads accessible on the wire connector. We can see that when the resistance increase button is pressed, the motor is sent about 4.8 volts and the motor begins to rotate. If we press the resistance down button, we can see that the motor now receives a negative 4.8 volts and the motor rotates in the opposite direction. To tell the console what resistance position the magnets are in, the motor has a position sensor that tells the console how far the motor has rotated. The console knows what position the motor needs to be in for each resistance level. The sensor works similarly to a dimmer switch for a room light. The more the motor rotates, the more voltage gets fed back to the console. Just like the more you turn a dimmer switch, the brighter the light in the room gets because it receives more power. The black, white, and red wires in the wire harness are connected to this sensor. The console sends a constant amount of power to the sensor across the black and red wires. If we put the probes of our multimeter on the red and black wires, we see the console is providing the sensor about 2.2 volts. The voltage being returned on the white wire tells the console how far the motor is turning. We can test this voltage by placing our probes on the white and black wires and reading the voltage. The voltage should read between 0 and 2.2 volts. As we raise and lower the resistance, this voltage reading changes to reflect the different motor positions for each resistance level on the console.